Hi. So when I started this project, I wanted to work on this power supply. This power supply is from the Icom 736. And I knew that this capacitor here, C10, was bad. It was bulging a little bit and the power supply had trouble starting up. So I went in and I replaced this. And I made some measurements to sort of show myself that I'd done the right thing. The problem is the way I made the measurements, and I made a major mistake, which has made this project take a lot longer than it should have. See, I had this awesome handheld oscilloscope. This is really a very, very cool piece of equipment. Highly recommend it. I really like it. And I was using it to make measurements on the switch mode power supply. Now, if you've ever worked on switch mode power supplies before, you know that usually the input does not go through any kind of transformer. It goes through a bridge rectifier. And then that becomes a ground. In North America, the neutral on an AC plug like this connects to ground at the breaker box. And so when you interface, meters and oscilloscopes and stuff with a circuit like this, you run the risk of connecting things inadvertently through your AC system. And that can have some bad consequences sometimes, as it did for me. The solution is to always run an isolation transformer when you're testing something like this. And I knew that, but I thought, oh, I'll just use a handheld meter because look, it's not connected to anything. It'll be okay. If I'm careful and I don't, touch the wires or touch other things, and I can make these measurements without consequence. But here's what I forgot. And this is so silly, but it's important. There's this plug on the side here for interfacing the meter to a computer. And I had this plug connected, okay? So in here, I had this USB-C plug connected like this. And I was transferring data off the scope onto the computer, which is really cool. You can get the picture or a spreadsheet of the data. It's amazing. And I had it sitting over here like this. And then I went to make a measurement on the board while it was powered with this. So I hooked this guy up right here. I went onto the circuit board with the probe and I made the measurement that I needed to right across capacitor C10, like that. I put the probe here, I powered up the board, and in that moment, as you'll see when I go over the schematic, I connected the ground of the computer through the meter over here to the ground of this little bootstrap supply. But because of the way the voltage doubler is in here and some other circuits, what that did is basically short out half the mains on the way this power supply generates its primary DC voltage. And that had the effect of blowing up this resistor right here. This is R1. Now when you look at the schematic, R1, and the silk screen shows this too, although it's covered up now, has a picture of a resistor and a fuse. And the reason for that is, in addition to helping with the inrush, that resistor stays in line with the circuit while it's powering on. So when you turn on the circuit board, all the current goes through that resistor. And if there's a fault, which there was because I had shorted it out, then that resistor will take the punishment and burn out and save the rest of the circuit. And so I'll show you how that is or why that is in a bit here. After I fixed this capacitor and I took care of my own problems, I replaced this resistor with a 20 ohm instead of a 10 ohm, but that's fine. It's only on for a moment and it doesn't dissipate much power nominally. I went ahead and replaced the other capacitors on the board here too. You can see those right here. These are new. A couple other ones. I think there's like 6 or 7 that I replaced here. This one, the capacitor I had didn't fit, so I had to drill out the holes and put it in, but it worked out okay. It's the same value actually. So yeah, let me jump over to the schematic and show exactly what's going on here with this.
So here we are looking at the Icom 736 power supply schematic. Here is the AC input. It goes through some basic RF and surge filtering. And it goes up here to a bridge rectifier. Now this is an interesting circuit. In the case of 240 volt connection like this, it's a standard bridge rectifier, and you get about 240 volts DC up here, and the ground of the rectifier goes right over here to this ground. In the case of 120 volts, this connection is made right here. And when you make that connection, you end up with what's called a Delron voltage doubler. I had to look that up on Wikipedia for the name of it. This voltage doubler uses these two capacitors. They get charged up, but they're in series, and so you end up with 240 volts up here, despite running 120 volts from the input down here. Now, I want to look real quick at my mistake before I go any further. So, I had attached my oscilloscope across this capacitor, which was bad, because I wanted to look at the startup current, the startup voltage on here. In doing so, my oscilloscope ground was connected to this ground, and that doesn't seem like such a bad thing, right? But in North America, this wire right here at the electrical box connects over to this wire, neutral to ground. And that's where the big mistake was made. So follow me here. Voltage comes up through here, just like that. Goes up into here. Now this being AC, it can go either way, back and forth, through this rectifier. So if it's negative, it goes over to here, okay? However, my oscilloscope was making this connection. And that's because, remember, this is connected to here, and this wire right here, which is neutral, has been connected to ground, which is over here. And so what this causes is the line voltage from the AC comes up through here and gets shorted out, goes back down through here. This is bad. This is really bad, because all the current the circuit needed came through my oscilloscope and my computer's USB connection, which seemed to work fine, but anyway. And then this resistor right here, which appropriately has been labeled with a fuse. It's a standard resistor, but it is being used as a fuse here. This burned up, as it should have. And because that burned up, it saved all these components from going through something really terrible. So it's a good thing it was there. All right, so under normal operation, when you're not shorting this power supply out, what happens? Well, you've got your 240 volts DC up here, and it's connected to the top of this primary winding on T1. This is the big transformer on the circuit board. The bottom of this coil, right here, is connected to Q1 and Q2. And when these transistors are turned on with their gates, right here gets pulled down to ground, right, through this resistor. And so by turning these transistors on and off, you're pulling this down and creating a waveform here. The waveform goes over here to the secondary side, gets rectified, these diodes, and filtered by these capacitors and this inductor. Okay, and we'll go over this more in a bit. The waveform also appears here on what is often called the bias winding. This waveform gets rectified, diode D3, and filtered with capacitor C10. If this capacitor is bad, then this is not going to be a clean waveform. In my case, it was intermittent, and it was occasionally shorting. And what that causes, check this out. This voltage here runs the 28 volt PWM chip. If you don't have this voltage, you can't turn this whole thing on, which turns off all of this. So you need this startup circuit to work properly. So once the waveform comes out here, it gets rectified, becomes DC, and it powers this chip here. You can kind of see that the PWM from this chip makes the power that runs this chip. That's done for efficiency reasons. You might wonder, though, what about when that waveform isn't on yet? Let's check that out. So if that waveform is off, there's nothing coming out over here. What happens is a little bit of this 240 volts gets divided down through this resistor, and this one to ground. The resulting voltage, about, I don't know, somewhere between 17 and 20 volts, comes down through here and turns on the chip through the voltage divider. And of course, that's also filtered by C10. So if C10 is failing, you won't get voltage here. Running that chip turns on the PWM, which creates a waveform here, which creates a waveform here, and then this takes over. This is a lower impedance source than this 100K stuff. So then the power supply is kind of running itself, as they say. And that's called a bootstrap circuit. The circuit has a little bit of a weakness, though, and that weakness is that this is unregulated, and this is just a voltage divider, which is also not regulated that well because resistors drift over time, and especially with heat. And so a better circuit might take this right here to a Zener diode to protect it against whatever the worst case voltage is on this chip, probably something like 25 or 30 volts. And if this Zener turns on, then no big deal. You've protected the controller chip, and the worst case scenario is these resistors burn up if they're really puny. And again, it saves the rest of the power supply. That wasn't done here, so if for some reason you end up with too much voltage here, or these resistors drift, or if R16 fails, then you're toast. You're going to burn stuff up. Okay, so how does this work? Well, the PWM signal makes a waveform over here. The waveform gets rectified, filtered, and by the way, these are not 100 picofarads. They're 1,000 microfarads. Somebody at Icom messed up. Every one of these electrolytics is labeled as a picofarad, and it should be a microfarad, and it should be 10 times higher. In any case, so we've got DC over here, but we need to regulate how much DC there is, and that's done with this optocoupler here, which connects to here. This voltage reference diode here, it's hooked up in an interesting way where the trim pin, which you use to set the voltage right here, is hooked up to the output of the power supply. That's what that is. And it's divided down through these resistors, and there's an adjustment where you can basically trim the 28 volts. When this turns on just right, and you've reached the proper voltage, this right here will turn on. You can now run this opto-isolator. When you turn on the opto-isolator, you run current over here. It gets pulled through pin 10 on this controller chip. And when that happens, the duty cycle of the output, which is on, abruptly comes off. You've reached enough voltage here, it can stop doing what it's doing. And so you get these shorter duty cycles. I'm not drawing this very well, but that's the duty cycle of this PWM waveform. If you haven't reached enough voltage, they stay on longer. And so you get a greater voltage there. That's a form of feedback for the voltage controller on this chip. There's also an OVP function. The OVP connects over to this. So these guys are connected together right here. The way the OVP works is there's a Zener diode at 25 volts right here, running off this 28 volts up here. Goes through a resistor and then through this opto-isolator. And if there's enough current going through here, it will turn on this OVP right here, and then this controller chip latches and it stays off. And that's good. If you have an over voltage condition, you really don't want the chip turning on and off and on and off. It latches that way, and it doesn't turn back on until the VCC right here is brought below the OVP, or just basically off. That's the best strategy here. Turn the thing off, reset it, turn it back on. The other way you can trigger the OVP is with this 100 degrees C temperature sensor on the heatsink. And when that turns on, this will also latch. That's a smart design here. Any temperature over condition situation will just shut the whole thing down. Okay, and then also we have over here a 13.8 volt output, right? The 13.8 is generated by taking the 28 volts from here, going through this Zener, down through here, and onto this controller chip. And this is a non-isolated configuration. You know, over here we have what's called a feed-forward isolated power supply. Over here is non-isolated. This PWM chip drives this FET right here. Feedback comes from this yellow line right here, which goes through these two resistors and this voltage adjustment into error amplifier number 1 on this chip. It has 2. Error amplifier number 2 on pin 15 is used to regulate the current. We've got these 0.1 ohm resistors here. Whenever you see 0.1, think it's probably looking at current, right? You can set the current with R62. There's also an error on the schematic. This connection should be there. It's not in the schematic. If this connection isn't here, then you don't have any feedback in this power supply and you're missing some of the filtration and it just won't work. So that's supposed to be connected there. One other cool thing about this power supply is it connects through the same OVP circuit that the 28 volt uses. So right here you see a 13 volt Zener and a resistor, and if there's enough current here, you'll turn this on and latch this and turn off the whole thing, which is really smart that they did that. One more feature I want to look at here is this relay. You see this relay here. Now when you turn on the IC-736, the switch is, you know, basically right here. Very shortly after you click this guy in, click, click, you'll hear this click up here for this relay. That happens because the 28 volt power supply turns on successfully and is able to turn on the coils here. And when that turns on, you bypass this resistor. It means it's safe to not limit the current going into the power supply. In my case, this relay didn't click on, and this resistor burned up over here and saved me. So this relay really serves a couple different purposes. One is to just limit the initial current surge, and the other one is to protect the circuit so that if this output is failing, we don't allow it to draw as much power as it possibly could. We limit that. It worked. Got the 13 volts. It's good. Did not get hot. Kind of nice that it turns on at 90% amps. Hardly anything going in. 4 watts. So there, let's run it at 115 in. Let's check here. See what we got. 29.08. It's great. So this is looking pretty good. The control voltage, which is where I shorted it out before, holding it about 12 volts, 11.3, something like that. Okay, that'll work. This resistor, not hot. Well, the relay clicked, so it's out of the circuit anyway. Current continues to be low, so that's great, 4.5 watts. And the output is 13.99 volts there, and 29 volts here, which is nominal. So I'm gonna call that success. All right, so since the last one was successful, I want to look at that control voltage startup and see how that bootstrap works, because I suspected some of the weird behavior we were seeing was from the old capacitor, which wasn't any good. And so we're going to look at the voltage right in here and see what that looks like on startup.
And to do that, we're going to use an oscilloscope and trigger it on the startup voltage itself. Now, unlike the last time I did this experiment, this is not hooked up to a computer, and that's important. If this is hooked up to a computer, it has ground through the mains, which switch mode power supplies don't like, especially on their isolated primary side. That side is running only off the AC power. It doesn't really have a concept of ground outside of this. So when you introduce that, given that the neutral is ground already, you're just hooking up the neutral line somewhere else in the circuit, and it doesn't like that at all. I mean, I can understand that. So if you're using a handheld oscilloscope like this thing, there it is. See, I'm not making this up. Don't shoot yourself in the foot by connecting this to a computer or to a power supply. It just isn't good. Okay. So with that said, let's set it up. So we're going to go to triggering and see DC coupling, single shot. Let's see, what's the level of the triggering? 2.2 volts rising edge. So that should be pretty good for a 10 volt supply, right? We're going to take this tip here and pull off a lot of this stuff on here so that it's just like this. We'll add a little ground to it. Ah, you've already lost it, right? Oh, there it is. All right, this little baggie here. These scope probes always come with little pieces, and basically you lose these pieces as soon as you make use of them. That's just life. There we go. Take this guy and put it on here. So that little spring can be bent so that it fits across whatever you want to measure. In our case, that's right there, from here to here, just like that. So to make that measurement, it will look different if the power supply has been off for a long time, because there's a little residual voltage on the capacitor, but we'll make the measurement anyway, and we'll just see what we see, because that's still very useful data. All right, so here's this. That get triggered somehow. Okay. And what is our horizontal time base here? Let's go for 1 second. I think the turn on is about half a second, so we should be able to capture it this way. Ready, set. It's pretty good. Okay.
So you can see here, this is capacitor 10 in the schematic. And this is the capacitor I replaced that was bulging, and it's part of the bootstrap startup circuit. And the data we just measured, I happened to take before the replacement and afterwards. And so prior to replacement, this is what a typical cold start would look like. And by cold start, I mean it hasn't been on for a while, and the room's actually cold too, because this is my garage. And on a warm start, this is how it would look. And by warm, I mean the power supply had been given a chance to turn on before. Maybe it was successful, maybe it wasn't, but there's a little bit of charge in the capacitor. And also this was taken when the room was a bit warmer. After the capacitor was replaced, this is how the startup curve looked. You can see that it's very smooth. There aren't any unexpected transitions here. And the ultimate DC that's reached when the PWM circuit starts up is very clean. And that's what we want to see. Before we reinstall the PSU, let's take a look at the noise.
I wanted to test the ripple. I forgot to do that. This will be an unloaded test, so it's not as good as it could be, but it's a good enough test for our purposes. Hook up here. power. Now let's go in here and measure output ripple. Do it again. Let's see. Channel 1, coupling AC. 1x, 20 megahertz bandwidth. Go for 200 millivolts per division on the scope. Let's see what we see here. Oh, that's very low. That's great. So 50 millivolts per division, we really are looking at about 25 millivolts of ripple. There we go. This is 10 millivolts per division. So you can see that's really not too bad for a switcher. It says it's 18, 20 millivolts of amplitude. That's great. Let's zoom in on the time base. Here it is. See if we can get this thing triggering. A little better. That is the ripple on the 12 volt supply. 10 millivolts per division. Let's check it out on the 28 volt line. We go right over to the ground on this supply. Right there. I'm going to reconnect the DMM on the bench here to make sure it's really working. Yeah, okay. So with it grounded this way, very, very low ripple. See. I'm sure you guys can see that. There we go. Showing 1.6 millivolts, which is kind of unbelievably low. But it's hooked up right. Okay, let's power it down.
After assembly, which I'll go over in a second, I measured the peak-to-peak ripple voltage on the 28 volt line. I was not very impressed. This is a significant amount of voltage, and it turned out that I was able to receive several of the harmonics on the HF band. Fortunately, the signals were very low, definitely below S1, and they were never a problem in actual practice. I was also able to vary the frequency simply by varying the line voltage, which would shift the frequency over slightly.
All right, so I got some of my favorite chemical here. I don't like to use this all the time because this stuff is very cancerous. But you know, we need it right here. So let's put a little in here. Of course, it went all over the place because kids play with it. Anyway. Let's just take that smudge right here and see what happens. Okay, that's enough of that. Let's put this in. I believe it went like this with the clips attaching it to this heatsink here. Ooh, dirty. Yeah, we're gonna clean that off too. Better. It's much better. This actually feels very smooth. So whatever. That's how that goes in. There it is. All right, let's see if I lost the screws or if I still have them. I think that's these. Maybe these? No, that's the case. I don't know what that is. Oh, that's the shield, internal shield. Okay, put that back. One, two, three, 4, 5, 6, 7 screws, I think. These black ones are for the IEC inlet on the back for power. These are the clips. Maybe I'll put the clips in first just to kind of stabilize the location. I think it was like that. All right, good. There's 2 of these that are different. One of the different ones goes here. Pretty sure. Let's put that in first. Now remember, don't tighten it yet. Just get it a hair above flush. You can always go around and tighten them when you're done. Forgot to mention this. One of the screw tabs broke off. It's right here. It was cracked when I got it, and it's going to stay that way. If I can find a washer, I'll put one on. If I can't, I won't. Not a big deal. That wire there is for the relay. That's good. I think we're good there. So I've got the one extra screw here, which goes there. I've got this one that I found on the bench, and it looks like it goes in here, but I don't know where it goes, so I'll save it. 2 clamps and the inlet screws. Let's see if I can find a washer. I'll go ahead and laugh, but the best I could come up with for a washer was this. It's a lug. It'll work. We just have to make sure, the lug doesn't touch anything, but otherwise it should be fine. Yeah, that's all right. I feel like it ought to be there because this board doesn't have a lot of screws. So let's go tighten everything down. I don't want to over torque that. Just a little bit. There we go. These two are good. Okay. Clamps. Some heat sink paste between these two would have been a good idea. But I guess it's a pretty efficient supply if it can handle it the way it is now. All right, now this guy goes on. Look at that horrendous solder job. We'll just pretend we didn't see it. No need for that to be too tight. Okay, now for the hookups. This one we have to open the faceplate to do, but the rest we should be able to do right now. Oh, grounding lug. Where does that one go? I'll check my old photos and see which place they stuck it. Oh, right there. There we go. That should be good. This connects to here. We don't really want these DC wires going too close to the AC wires. But it's kind of unavoidable here because right here, this is the line, right? So something like that might be good. Always look carefully. Bring these wires back around. But you know what? That's probably a good time to open up the front panel. So we take off this bottom piece. Isn't that pretty? Ooh, all right. These guys here come off. I need a book to put this on. Book isn't such a good idea, actually. Open that up carefully. There's a little service loop here on this wire, right there, see that? We're gonna go right in here to that connector. Looks good. While we're in here, scan over all the wires. The VFO one looks super loose. I have to push that in a little bit. There we go. Okay. That should work. I have the 736 hooked up to Variac current limited supply, and we're going to turn it on at about 100 volts AC. It's on.
I do have one that is pretty high. I can't tell a lot of difference in the gain, and I have done field measurements on them on takeoff angles and stuff. They're W6 Echo Lima K0 United Ocean.
W6EL testing. W6EL testing 1, 2. So yeah, everything's working. It's performing as well as it ever did. Sensitivity's on par. I tested that earlier. I think I call that a success. And the next thing we're going to work on is the display unit, so that we can see the menus and the frequencies and everything on the display.
Did you enjoy this video? Let me know in the comments. I'd love to hear from you. And be sure to stick around for part 3, where we replace the display. Thank you.
Tiene un tipo así como multifunciones, ¿verdad?